Hi, I'm Sam, and I'll be talking about the Superstructures assignment for Structures 2, in which myself and Song Yin designed a domestic shed. By doing this assignment, we've gained a greater understanding of the structural design process involved with superstructures. This will allow us to work more effectively with engineers within the construction industry. For Part A, we were given a wind speed region of B, a wind terrain category of 1, partial shielding type, and the T3 topographical effects to base our calculations from. From this, the wind class was calculated to be N5. This was done using the Australian Standards 4055 2012 Table 2.2, table as shown with the wind class highlighted. Australian Standards 4055 2012 Table 2.1a, as shown, was used to calculate the serviceability limit and ultimate limit state speeds. Australian Standard 4055 2012 Table 3.1 was used to calculate the net pressure coefficient for general roof areas, which was found to be -1 and positive 0.63. This is highlighted as shown. From this, the pressure calculations for serviceability limit state and ultimate limit state were done. The net pressure coefficients were then found for the walls as shown, and suction and pressure were calculated for serviceability limit state and ultimate limit state. After this had been completed, we were able to design our purlins and girts. Roof sheeting used was to be Lysort trim deck, giving us a mass of 4.3 kilograms per meter squared for our roof sheeting, and the inclined spacing was 1900 millimeters. The first steps included calculations of the dead loads, live loads, and wind loads. These were then combined together, and a suitable purlin was selected from the capacity tables. A Z250 24 purlin type was selected, and the serviceability of this member was checked and found to be adequate. For girt calculations, the wall sheeting to be used was a Lysort trim deck with a mass of 4.3 kilograms per meter squared, and the spacing of wall supports were to be 3000 millimeters. There is no dead load or live load for girts, as they are horizontal structural members and only resist wind loads. Therefore, the wind load is calculated for ultimate and serviceability states as 3.29 and 1.33 kilopascals. Load calculations were calculated for purlin and girt line loads for each design member. The inward and outward loading was then checked against, leading us to choose a Z350-30 girt from the capacity table using a 6 meter span and 1 row bridging. The final step of member selection was to check if the size of the purlin was adequate. If not, a larger section would have to be chosen and rechecked. The member sizing was found to meet requirements and also be economical. Part B, final submission. Part of this assignment involved a site visit to the UniSA Mawson Lakes campus. This gave us the opportunity to take photos of a portal frame structure and also see a real-world example of what we had designed by using what has already been taught at university. Here are photos inside of the structure, showing the columns, rafters, bracing, and side rails. In these photos can be seen columns. These are vertical structural members that transfer loads from the roof to the foundation through compression. Beams are horizontal structural members which carry transverse loads. These are loads applied perpendicular to the longitudinal axis of the member and cause bending and deflection. Rafters are beam members that support the roof system. Bracing can be angles, rods, or cables in the roof and transmit loads to the foundation. Secondary steelwork are members that connect and restrain the primary steel frame. It includes girts for the walls and purlins for the roof, which support the roof and wall cladding, and transfer loads from the cladding to the primary steel frame. The basic connection members of industrial building and shed are apex connections, corner connections, and base connections. They provide connections between rafters and columns and footings respectively. Afterwards, we were also given the opportunity to see the mixing of concrete. Different types of aggregates were also shown. The mixing process and a slump test of concrete was also shown. The slump test concrete is left to cure for 28 days. It is then tested through a compression test to check for the MPa. Building stability under wind. The compressive and tensile forces for roof and wall bracing under wind were calculated. This was done for windward and leeward wind pressures. Individual tensile and compression forces for each member was calculated and is shown in the following image. Design of the central and end rafters. Calculation of the dead load, live load, and wind loads, and then the total combination of all three was combined. Design capacity tables were then used to choose a suitable member. For the central rafter, we chose a 460 UB 67.1, and the end rafters were a 360 UB 44.7. The reasoning for why the central rafter type is larger is due to the central rafter supporting twice the area than the end rafters. Due to this, the central rafter is under more deflection than the others. Compared to other alternatives on the capacity tables, this choice gives adequate safety whilst also having the lowest weight compared to the others, making this the best choice for rafters. For columns, a 150 UB 23.4 was selected to support the central rafter. These intermediate columns need to be larger than the end columns as they carry more load. For this selection, there aren't many similar alternatives on the capacity table, but the 150 UB 23.4 is still the best choice as it is strong enough whilst being the lightest. This reduces materials needed and also saves money on purchasing costs. Here is a sketch showing the gravitational and lateral loads for our shed. This drawing shows the member types we selected through the assignment. A 5.2 metre high shed spanning 10 metres with columns spaced at 6 metres, an intermediate column being a 150 UC 23.4. Here is our member schedule showing member types and section types used throughout the project. In conclusion, this project involved the design of roof members and columns for a portal frame shed. To design each item, we had to calculate the dead load, live load, and wind loads. Then used the result of all of these to select a suitable member from the capacity tables. This would need to be checked for safety and if the selection is economical for the building. If not, the member would need to be changed and then checked again until a safe and economical member was found.